Friends, Romans, DAC attendees, lend me your ears. It's day 2 of the 59th DAC Poster Gladiator competition. If you were here yesterday, you have the idea. If you weren't, here's how this plays out. We have a series of poster presentations. They'll come up. They have 10 minutes to present tops. Our panel of august judges will then quiz them with very, very hard questions, and we go on to the next one. Then they vote. Now, I forgot this yesterday, but today in the DAC app, if you go to Posted Gladiators at the bottom, click on that, and you have the ability to cast your own vote too. So let's do that and make it a group thing. I'm Brian Fuller, Editor-in-Chief at ARM, and let me introduce our august panel of judges, starting with Mac McNamara. They're all former DAC chairmen. Mac McNamara, Rob Aiken, Joie Lee, Harry Foster. They're tough. They're tough Roman emperors on these poor people. Our first presenter is going to be Lakshmanan Balasubramanian from TI and his team.
Good evening. This is a presentation on optimization of the efficient power-aware verification framework for mixed signal low power SOCs. I have a huge list of co-authors here, contributors from the slew of domains across mixed signal SOC implementation flows, verification, standard cell backplane, all of that contributed to this work. Myself and Gaurav are here to present this. To start with, we do have a timeline view of the execution that's shown on the top. So conventionally, this is set in a context very specific to power managed, low power, mixed signal SOCs with significant analog mixed signal integration, including on-chip power supplies, on-chip oscillators, slew of oscillators from all the way from real-time clock to high frequencies, and then a lot of analog data path, RF. All this is integrated with significant amount of singular multi-CPU embedded processor. Right? So with that context, of course, the pictures are not very readable, but the intent is not to go to the details of them. Conventional design verification approach involves it starts with the RTL design verification. As soon as the first RTL is up, and you may have the first integration, and then you start doing the verification of that. It's highlighted in the complex flow that's shown here, right? And then followed by, it proceeds to power-aware RTL where the power intent is ready. For some reason, the method that's explained here is compatible between the standard CPF as well as UPF-based flows. Then the low power readiness, because of this, the sequential nature that you take, the low power design readiness, the maturity is delayed. Now you have post-synthesis, you will get a non-power aware gate level view, and you will start with the zero delay versions of them to start the sanity checks, then proceed on to design and timing closure, and then do a timed but non-power aware GLS. This is what is conventionally done in industry. There have been recent publications outside my team, from outside across the industry. This has been a very consistent flow approach across it. What I'm going to present is a very commonsensical approach. I don't know why others have not taken it. So, but we'll come to that. It requires some of the novel underlying components, but the approach is pretty commonsensical. So what's done? What are the challenges associated with that? Especially when you have a mixed signal integration, the hard IPs, which includes the mixed signal IPs, on-chip memories, including non-volatile memories, and the GPIOs and all that stuff, they may contain a lot of digital content inside, right? Depending on the richness of the mixed signal IP, the internal digital contents may have to go through their own semi-custom design flow to harden before they are available. And the timing closure for them are done in a hierarchical fashion. They are done at IP level first, and then they're integrated, an abstract view is created and then integrated at SOC level. And hard IP should always be a fully implemented view, whether you are in RTL stage or gate level stage of SOC, right? That's how it's always considered. The zero delay netlist and analog and digital interface timing captured as behavioral timings, so they cannot go through a custom .lib based approaches of timing, SDF based approaches. Fully timed abstraction is used in SOC level. SDF annotation issues are very common, especially in the first platform design, if there are common standard cells used inside the hard IPs as well as externally. Right? And handling and maintenance overheads for various versions of this, including we have RTL, PARTL, GLS, PAGLS, timed, non-timed, various analog IPs. So much of deliverables, so many flavors, it adds to a complexity. Repeated generation of this and maintenance is overhead, as I told you. It results in longer DV cycle, multiple DV execution flavors, as well as purely digital low power systems can live with this, but in a mixed signal context, it creates a huge bottleneck, especially with limited scope of PARTL at the DV stage and late findings that can occur post RTL and the implementation phases. There are again references to what's done here and what are presented here. This again shows a conventional view. What are we going to change here? First, the goal is to minimize the number of abstraction flavors as well as the design verification complexity. What do we do? It's applicable for all the power intent formats that we are using here. The low power mixed signal development involves either CPF or UPF. Usually what we have seen in the experience of last 2-3 years, if you have a focused effort and right approach to execution, the power intent can be ready within a week's time from the RTL readiness. But somehow it's never done that way. You do RTL and then do significant amount of functional verification before you even start looking at power intents. But both are design components which have to go hand in hand, especially in the context of mixed signal, right? So can I use that fact, right, and enforce PA-RTL readiness before you start the RTL, maybe with the overhead of 1 week in a big 1 year or a 6 month cycle time, avoid non-PA-RTL flavor altogether. These are some of the critical components that enable this. I won't go through all of them. It can be read through later. Some of them include a very novel approach of enabling design CPF or UPF for hard IPs with novel components that enable verification at a very early stage. Without that, it's not possible if they are power managed IPs. And there are other common stuff that's done here. Then you move on to, as you see here, we avoid the PA-RTL, the RTL DV is avoided. Okay, as you see here now, the PA-RTL, the timeline moved because I completely avoided the RTL stage. Now we go to the gate level stage. I also want to avoid the non-power aware gate level stage, right? Again, there are critical components that enable this. I won't again go through all the details of them, but the main thing is the power aware models being available for all the IPs at timely manner. And there are SDF annotation issues. There are targeted methods, very practical methods to attach them. I won't again go to the details of them. We do a flat STA or a timing closure, which looks at both the IP internals of the digital sections of the IP internals and SOC level together to take care of in-context timing closure with appropriate deliverables, of course, from IPs. With that, we are able to achieve avoidance of PAGLS and just do non-power aware GLS and just do PAGLS, right? With that, as you see, all the timelines move ahead, upfront, they become earlier. And then this method is actually applied on industrial SOC design, not just on iterative designs, on a first platform design of 65 and 45 nanometer designs. And then it benefits, subsequent variant spin designs benefit much more than the platform designs here because of the heavy reuse of the past components. We could achieve RTL freeze by at least 2 months ahead of any conventional method before. Avoided executing all these unnecessary flavors. Easy maintenance of IPs, very limited number of IP deliverables that needs to be maintained and flavors need to be maintained. Quality improvement, especially because one of the biggest problems is when it comes to mixed signal integration, especially if there are mixed signal power supplies on chip, their settling times, analog settling times, and if they have a critical interdependence to timed digital paths between analog and digital interface, that can never be done in a non-power aware GLS based methods, right, or non-power aware RTL based methods. This requires this flow. Otherwise, they involve custom checks at the implementation stage, all those are avoided. So all this can be now done in a much more seamless fashion. These are just the quantifications of the benefits. That's where I have. Thank you very much for the interest.
Thank you. Harry, you get the first question. We get about 2 minutes.
2 minutes. Okay. But actually, my question is more of a clarification. I understand in the pure digital world the type of requirements I want to associated with power, for example, retention, power up, power down, transition states. Can you give us some examples of the types of requirements that are unique to mixed signal?
Very typical. You have, for example, in external power, primary power supply comes in, and then you have an on-chip LDO or DC-DC regulator or whatever, creates additional voltage domains, and then subsequently they create power switches on chip coming from power intent. The LDO or DC-DC is a mixed signal component coming in the power path, right? And then that creates additional switch domains subsequently down the line. So the power up itself is very critical. The timing interdependencies and all of that. Power up is a very, very critical path in analog integration. And especially that's not automatically taken care of in a semi-custom implementation flows.
Is there actually requirements that cannot be described through CPF or UPF?
They are described in CPF, but we work closely with our EDA vendor partner Cadence to go beyond the standards. And I'm also working in the UPF standards committee to take those requirements also to UPF. Today, UPF cannot handle that. CPF can handle that by violating or going beyond the standards.
So just a quick question. It looks like basically what you did is you said, let's do power-aware stuff instead of non-power-aware, right? That's basically...
Yeah.
So why do you think no one had done that where you were
There are
before?
challenges in CPF. There are some publications that I've shown there, which are done going beyond the standard and working with the vendor to enable such methodologies, such capabilities in the tool, which have not existed before.
Okay, and where did your libraries come from? Were they internal or commercial?
This is commercial. Initially, we start with internal prototypes, and then over a year period or whatever, we work with Cadence to get those features implemented in commercial tools. And then later, CPF, of course, is kind of a quote-unquote dead standard. We are driving that in the UPF standards, so hopefully they will become now all vendors can get these features up and running. Thank you.
All right, let's give Lakshmanan and his team a round of applause. Thank you. All right, next up is a presenter that was on the schedule for yesterday but had a conflict. So today, at this time, we are going to hear a unified IP QA methodology to improve validation coverage and throughput from ST Micro and Siemens EDA, presented by Wei Ling Tan from Siemens EDA.
Hi everyone, my name is Wei Li Tan and I'm from Siemens EDA. Today I'd like to present the Gladiator poster session for a unified IP QA methodology to improve validation coverage and throughput. This is a collaborative effort from Gitanjali Sharma, Jean-François Lipika Pawani, Lionel Kuder, and myself. And my esteemed colleague Lipika Pawani wanted to present here. Unfortunately, she couldn't make it, so I am here presenting on her behalf. So the motivation onto this is that in every design flow, there are, I would say, at any point in time, about a dozen different design views and formats that get generated and passed on from one tool to another. And a lot of times, these views and formats, I'll get to a couple of them in a minute, like LEF, DEF, GDS2, CPF, and UPF that was mentioned just now. They're all created by different processes, as in different workflows, by different people in the team, maybe different teams altogether. And they're mostly non-uniform in terms of the creation as well as how they contain different information. So how do we have a system that consistently checks for all the issues that may hide in these different formats and make sure they're consistent with each other when the size of our IPs are growing, the number of formats that we deal with are growing, and so forth. So that's the motivation of coming up with this methodology. This just shows us kind of an example of how ST's, sorry for the formatting on this slide, what's ST's process of workflow in creating these different views, right? You create the electrical views, you have the physical models, functional views, DFT views, and other. I'll take physical models, for example. You have left, def, GDS2, right? The apps from all the way from abstracts to full detailed layouts. And then you have electrical models like timing, like power, like noise, your CCS, NLDM, LVF, and all these contain data. All these contain different aspects of a design that need to work together perfectly, I would say, in order for a design to be taped out successfully. This means that months, sometimes maybe even bordering on years of design tape-out work are all contingent on all these formats agreeing with each other, being consistent with each other, and like I mentioned, being perfect, right, in terms of correctness. A simple example. Let's take a look at left, Verilog, layout, Liberty. These are files that come from different parts of the different people create these files. Maybe different organizations in the company create these different files. And one simple example is this area field that you have in your Liberty that I'm showing over here. It's very, this is one of the many different fields that we have. But area in Liberty is actually a field, a value that comes from the actual area of our layout. So the definitive correct answer of what that area should be would be in your GDS. Now, however, that GDS gets abstracted into a left, and who knows? Who knows whether or not the area in your .lib is the actual area if you look up the GDS, if they're correct or not. So there has to be a methodology that consistently checks through this. What happens if somehow this slips through our net and somehow makes it into a design tape-out, and you run PNR using this set of left and Verilog and GDS and Liberty? Well, for the most part, the PNR tools usually will allow this to pass because, hey, syntax is correct. I'm going to, let's go and do our heuristics, our implementation. At the very best case, you may cache this after your final LVS, which means that we've wasted months of our design closure time. The worst case, this might not even be caught. So at the end of the tape out, you might think everything's done correctly, but the design is suboptimal. It's not optimized correctly because all the optimization engines had the incorrect information. So this is just one of many things that could go wrong, and we call it soft error. We might not even know about it even after tape out. So the methodology that's being used over here, it uses one of the technologies that we have in Siemens called the Solido crosscheck. But what ST really wanted to do is take that technology and make it immediately deployable to hundreds of designers, right? So that these designers don't really need to know what's going under the hood. Designers can just take the IP, the different formats and views, and through a web interface, almost push a button, and the tool will handle all, syncing up all the data, linking them together, and make it so that this technology is available as widely as possible to all the different designers in the company. And that's why what ST did was add what they call the ST's CAD infrastructure on top of Solido crosscheck. So Solido crosscheck engine, it has many built-in checks in it, and you can use it to run consistency checks and correctness checks for all the different formats. ST took that, and they wanted to meet breadth of coverage. They wanted to cover all the technologies in ST, usability, configurability, and most of all, scalability to the entire company. So what that means is they added, and using the API interface, they added this CAD infrastructure on top of what Solido Crosscheck offers. So users see a web interface, and users are able to very quickly access all the checks that they need to do for all the different IP types. All right, results. A couple of examples that they did because of this. I'll just go through the one on the example number 2 in the interest of time. Layer maps. Every process, every design has their own set of layer maps. What layer constitutes maps to what layer in GDS. So because ST is building this for an internal audience, ST knows what the different layer maps correspond to. And that's one of the examples of how a CAD organization can make verification tools be used more seamlessly and more effortlessly by designers in that company. I guess example number 1 is where you can ST actually built the capability to launch third-party tools, read in the information and results of checks on those third-party tools, and display them in the same dashboard. The results is that this methodology now has gone through many tape-outs and I think many designs. I think I discussed this with Lipika earlier. The best QA methodology is the one you never see, right? Because it's the one where you just run, well, everything works fine at the end because the QA methodology did its job. But Lipika and team actually pointed out all the different issues that they caught that if it were not for this methodology would have made it to the tape out. And you can see this all the way ranging from packaging issues, spec issues, syntax issues, design issues. So all of these are able to be caught once you really apply a consistent methodology that can be used, that includes all the different, that can be used across all the design teams in the company, across every tape out. So the summary is IPQA is complex because of the amount of data, sheer amount of data, and the number of formats we need to take into account. Utilizing a consistent single pipeline is always the best method because you've got everything going through the same funnel. That way you catch all the issues before they go into tape out or a stage where you need to spend a lot of time and effort to backtrack on issues. And for future work and discussion, we're working with ST on version to version QA. What's different between the next revision of my design and this revision? We're also working to integrate Solido Crosscheck at all different stages of design. Maybe other portions that may be considered sign-off. Right? We want to include that in the same dashboard. And last of all, right? Last but not least, also job splitting and basically making these checks go faster by being able to automatically split and fan out jobs to different compute nodes in the cluster. With that, thank you, everyone. I'll open it up for questions.
Yep, we got about a minute or so for questions, so fire away, gentlemen.
I have one just on things that appear to be inconsistencies, but may just be the result of the format. So, for example, bidirectional pins, some tools don't know about them, don't want to know about them. Mm-hmm. Yet the library model for that cell will list it typically as an output or something. How does this methodology deal with that?
So in every QA methodology, there will be what we call, if the format itself or the tool itself doesn't care about whether or not your pins are labeled as in, out, or in or out, one good way, and there's going to be many of these situations. Oh, this tool doesn't care. I don't really care about this. One way the methodology deals with this is by employing waivers. So if there's a certain thing that you know applies to our specific use case, and we know it's not going to be an issue. I know the syntax has in and out, and my design files are different. I know they're different. I know my tool doesn't care. I can waive that, and that's why we employ a system of waivers. One thing that we do also is every waiver has to have a reason, has to have a person's name attached to it, so you have accountability there. But yes, then you can employ this method to make sure that it doesn't bog down your whole system with fake errors.
Yeah, I was thinking, especially with ST, that somebody's name needs to be on the line, right? If you gave a waiver here, then it has to be paid later. Yep. And can you write your own rules or own extra checks and things? I mean, is it extensible by the user? Or?
Yeah. In fact, the tool itself allows for custom checks to be written in via Python, so you can actually import your own Python rule checks. And that's actually how the number of checks in the tool grew. And ST also helped a lot on that. They had situations where I want to check this particular thing. Oh, sure, go ahead. Atul is from ST, so maybe he can answer that.
I'm from ST, so yeah, you're absolutely right. So
Right.
we are actually able to write our own APIs and own checks.
Very good.
And the good part is, what cross-check does is that the report that you finally get is consistent. So it's easy for the QA manager to just look at the report, say everything is clean, check mark, let's go ahead.
The layout that you showed was like 45 nanometer or greater. Do you see that this methodology works better on older nodes or newer nodes, or is there any difference?
I don't think so there's any difference, because the number of views is almost the same. However, the newer technologies, some views have added on, but overall I think it's all good. It's across the board.
All right. Well, let's give this team a round of applause. Thank you very much. And next up is using formal verification sign-off for digital IP. It's going to be presented by David Vincenzoni from ST Micro.
Hello, good afternoon. I have 5 minutes to show you why the formal verification is better than a UVM methodology that we use until now. Okay, I show you why the formal verification is better than the UVM methodology that we used until now, and allow us to save efforts and discover more bugs. The UVM languages are efficient. They allow us to build a complex constrained random test, but need a long learning curve. The formal verification allows us to do an exhaustive verification of our code, saving efforts from 60 to 80% as compared with classical dynamic approach. The concept that we learned with UVM, the use of verification IPs, the use of scoreboards, can be reused also in the formal flow. So we see how we apply the same steps of UVM in the formal sign-off methodology. So let's jump to the formal. This is our flow. The first step is the linting, so a static check of RTL, where we are going to clean the code in early stage and checking the dead codes, checking the FSM coverage, the FSM deadlock or live lock, and also the DFT checks. Next step is the clock domain crossing needed for the peripheral that use asynchronous clock domains. The protocols are verified by using assertion-based verification IPs. Configuration register and status are verified by using a specific formal app. All the features of our block are verified by writing system verilog assertion and prove them with the formal property verification tool. At the end of the flow, as we do for UVM, we extract the RTL code coverage. Here we see a comparison between UVM and formal. So the RTL can be seen as a state space, and the target is to cover all the states and all the legal transactions. So with UVM, we are able to cover a subset of this space, while with formal, we cover them exhaustively. The first case is a flash interface. It is formed by two HB slave ports for reading the memories. one port for command and configurations. There is the arbiter that arbitrates between different access requests, and send the request to the FSM that generate a transaction for accessing the flash. The test bench has a structure similar to a UVM. We have verification IPs. In this case, these are assertion-based verification IP. So the master, the slave are built with assertions, covers, and assumes. The data are verified, the data coherency are verified with a scoreboard that is a formal scoreboard. And we develop a verification plan as we do for UVM methodology. The second example is a CPU fetching buffer. It has a slave HB interface for reading data and a master interface HB. There is a FIFO that performs data adaptations that works with two different clocks that are rising edge aligned. The verification test bench has a structure similar to the previous one. We use the assertion-based verification IPs for the master and slave, and we verify the data coherency with another scoreboards. We also added some SVA assertion for checking the FIFO properties and the data ordering in this case. At the end of the flow, we extract the coverage that is a formal, RTL formal coverage. For example, in this case, we see a lack of cover for a block that is the configuration register. This part is covered by the specific formal app, for example. And we merge, as we do in UVM, in this case, we merge the different formal proofs coming from all our flow, and we extract the overall coverage that in this case is above of 99%. So with the formal approach, we shorten the verification effort, saving from 60 to 8%. When the formal is applicable, we can save weeks of verification. And the formal allows us to discover tricky issues and find out more bugs than any constrained random test. Thank you.
Thanks, David. All right, time to run the gauntlet here.
So a question I have, certainly when you get into formal property checking and assertion-based verification to a lesser extent, is what do you do to validate your constraints? Because everything falls apart if the constraints are not correct.
Yes, usually in formal, the constraints, sometimes the constraints are very easy, for example, are DFT, so I enable only the functional path, but for the protocol or for the flash, when we have to design the constraints, we usually verify with a simulation, dynamic simulations. This is the, let's say, common way. So, because at top level, a system on chip level, we develop, of course, dynamic test. We use part of formal for connectivity checks, for example, and reachability. But we can run dynamic, and usually we verify the complex, the tricky constraints in this way.
So I'm actually not expert on the formal, but just make sure I understand it's the main new thing here. You just apply the formal to the methodology, and that's basically, or you add something on top of the, like say, normal formal verification.
Sorry, I didn't catch it.
like I try to understand the main, the main innovation here, like the new thing here. Do you just like apply the traditional form modification brain to this IP part, or there's something on top of the traditional form modification you added? That's my main question.
Yeah, so let's say using the formal flow for signing off the IP help us to reduce a lot the effort. This is, let's say, the main advantage. So signing off the IP with formal. Or maybe I didn't catch the question.
So that's the innovation. You're pulling the formal into the the more traditional coverage-based metrics, and have you done this test case? You're integrating formal into that same list of these more informal methods. Is that the innovation?
Yeah.
I like formal. Yeah, I wore a tie today.
We like formal. Good.
Any more questions, gentlemen? If not, let's give David a round of applause. Thank you.
Thank you.
All right. Now, next up is machine learning techniques for PDK development efficiency, presented by Romain Foyet and from his team at Global Foundries. Welcome.
Test. Okay. Oh, hi. Hey, Danny. Nice to meet you. How are you doing today? Welcome to the team. Hey, Jack. Yeah, nice to meet you too. I'm good. I'm pretty excited to start coding P-Cell today. Well, that's the spirit. So, to code that P-Cell, we would usually use like about 4 days. But that customer, he wants it tomorrow evening. Okay. And by the way, you need to use all our best practice. This is really important to our PDK quality. They're all listed in here. Okay, how much time is this going to take me? It's about 100 of them, 30 minutes for each. That's 50 hours. So I have to do that and code the P-Cell for tomorrow evening. You got it, Danny. Good luck. Okay, so that's my introduction. This is the problem statement of this talk. My name is Romain Foyet. I'm going to be talking about machine learning techniques for PDK development efficiency. This is a team effort. My colleagues here are not here, but Nolan, Pavek, and Vivian Miller make great contribution to this work. So P-cells are layer generators. They are a key component of process DDN kits, also known as PDKs, and our continuous improvement process fosters our team to learn from their challenges and compounds the benefit into a higher level of quality. And the keystone of that process is our best practice document. The challenge, though, with that document is that it's big and keeps growing. And so there are like two situations we want to avoid. The first one is our developer, usually a new developer, will say, okay, I'm going to review all the best practices, but they're going to deliver the P-Cell late. The other situation we want to avoid is a developer that says, well, I'm never going to have time to do this. I'm just going to do the P-Cell, and they're just like, going to forget about this. And that's not good because quality goes down. So what should we do? This is when this guy comes in. You remember that movie, 1991, Terminator 2? Okay, he's the good Terminator. He's the one that helps the humans. And this is what we're doing here. We build a machine learning model that helps the developers. So how do we do that? We, again, back to this, we don't tell the developers, hey, check all of that before even you get started with working. Instead, the machine learning model is going to look at that P-Cell and tell the developer, you know what, just check page this, page that, you're good to go. Just 2 pages instead of 100. So that's how we help the developers. This is an example of best practice here with like a coding style of like algebraic versus prefix. And for that, we used a naive-based classifier. So it's very similar to your spam detector in your email account, right? So, and what's really it's been exciting in that project is that through exploring different best practice detection in our proof of concept, we stumbled upon the opportunity to add predictive text to our developers' toolbox. So, you guys look up stuff on Google, right? And you put 2 words, and Google tells you like the whole sentence even before you think about it. We're trying to do that with skill coding when our people code P-cells, right? So, obviously, big benefit of adapting to new coding styles. It's not limited to a static list of functions. It really adapts to all the teams, the way they code. And also, it's not limited to one word. Our results are pretty encouraging for that proof of concept. We have 95% accuracy on the best practice detection and 70% accuracy on the predictive text. This graph shows here, of course, if you reduce the number of characters, you're going to have less accuracy, but it's actually good to see that with about 5 to 6 characters, you can reach the max of accuracy. Our future work will be focused on transitioning from a proof of concept into a production-ready tool. For the predictive text, we will want to increase our speed of production, and we will want to spend efforts also on making the user interface improved to really touch as many developers as possible. When I attended DAC 2020 virtually, one presentation made a big impression upon me. It was a Sky Talk titled "Succeeding with AI Today and Tomorrow." It was by Toby Capello. And so in his talk, Mr. Capello shared a quote from the Harvard Business Review. It was saying, I quote, "Over the next decade, AI won't replace managers, but the managers who use AI will replace those who won't." So I took that advice to heart, and I'm really glad I did. Exploring AI with my team has been both rewarding and very exciting. To describe our journey with AI, I will leave you with the famous quote from John Campbell, which, by the way, inspired George Lucas for Star Wars. And I quote, "The cave you fear to enter holds the treasure you seek." Thank you.
Very nice, very nice. And I'm impressed that you went out and changed your first name to better compete in the context of this competition. Judges.
Which ML toolbox did you use to build your system?
All Python. It's all Python.
Okay, so but which libraries in Python? Any?
Sklearn. Yeah.
Okay.
Sklearn, and like one of the snapshots we see here on the right. This is actually the PyCharm interface. So that was like our first interface that we're using, and that's why I talk about in the future we want to have a direct skill interface. We don't want our developers to have to go look into the Python PyCharm. This is our prototype, but you would think that the complex part of this would be machine learning, but we did that already, and it was not that complex because these libraries in Python are just all there, right? So it was not that hard. Now the hard part for us, and we started, but it's becoming hard, is to hook it up into skill.
Yeah. So do you think from this that you will identify weak points in the P-cell construction methodology that are more vulnerable to problems?
So from the 2 parts, right? There's the best practice and there's the predictive test, and I have an answer for both. For the best practice, again, we want to push standards. We have a growing team, and we can just teach them every single details. The best practice does that, and our machine learning kind of mentors them into doing that with a specific code. And so that's how we like improve quality, because we've thought about, we have like our experts sat together, this is the best practice. Now for predictive text, not only we are hoping that it's gonna speed up the coding, obviously like they can code faster, but also I'm sure everyone who has code here has spent 3 days debugging and realizing, there was a typo, right? We all have done that. Well, that doesn't happen anymore. When you have that generated line, there's not a typo in it. So that's my answer. We will have great hopes for that, yeah.
I mean, there's not a typo, but there's maybe a selection of something that, was not quite the right word, but it syntax is correct, and you're off to the races with not the correct intent, right? So you rapidly create perfectly good English or skill that is not correct.
Yeah, no, and to be clear here, this is what I was trying to show here with Terminator. We're helping the human. We're not replacing the human. So we definitely have, as Anirudh was saying this morning, the truck driver becomes a monitor of 15 trucks, but he still monitors them. So that's the same thing. We would have the developer look at, what are the suggestions here? Yes, no, this is what I wanted to do. And you're right that maybe we'll come into cases where maybe the decision will be too quick. They'll think that's what they want to do, but they didn't catch that, it was actually similar to what I wanted to do. But
I think you need to bring verification or simulation of the results of it in almost right away to catch this.
Definitely.
Because we've done that like in the phone where you just select the suggested word just for fun and chat with your buddy, or pick the second one, and it's really, it can be sort of weirdly fun, right? As it picks like, but so there's a, because somebody didn't enter it all by themselves, you got to pull that verification much sooner, I think.
Definitely. I agree with that,
So I have a question for our next page. Just how do you, for example, for the predictive text, right? If you capture the error, right? If it's correct, it's okay. So how do you define this as 70% accuracy?
That's when we define it by you predicted what you intend to predict, right?
The first prediction is
so you intentionally actually made it sound try to fool the tool, then to get it. Because let's say with new people, right? He didn't even know, what he's trying to do, right?
We didn't
just capture the typo or not.
We didn't try to trick the tool. And to be clear here, we're all in a very proof of concept, right? It's very first prototype. And I'm really hoping to get a lot more data, right? As we get further and using more fancy metrics that we have a lot of them in machine learning. But here it was more really basically hey, we want to predict what you wanted to write. Did we do it? Yes, no. And it was more that we were looking at. And it was more about really what we're showing here, how many characters do we need before we can have an acceptable level of prediction. That was really what we cared about. Because also here we're 95% best practice and 70% is our top here. But we expected that. This is a lot harder to predict what the developer is going to type as opposed to, did you use the best practice? Yes, no, right? That spam detector is easier, so yeah.
Well, some of it you find out that the language is poorly chosen. So it has 3 different operators that are spelled very similarly at the beginning, but they mean different things. It can be let's go fix the language so it's easier to disambiguate.
No, it could, you're right. Yeah. That's a good point.
As a final question, did you minor in theater?
What?
Did you minor in theater?
I was his major.
I did not, but I did a little bit of a theater in college. Just a little bit, yeah.
I like the prop of the book. It's
This is not the book, but it's the book I'm reading right now.
If you brought the real book, you'd be in trouble. That'd be the
exactly
proprietary information.
Facilitator's Guide to Participatory Decision Making. Excellent book. Well, thank you, Roman, very much.
Thank you, guys. Thank you.
On to our next presenter. All right, our next presenter is going to discuss technology co-optimization to mitigate the technology impact of context-based timing and standard cell library. This is Rohit from ST Micro, which has flooded the zone today.
Hello, good evening everyone. So I would be presenting my poster on design technology co-optimization to mitigate the impact of context-based timing. So I would like to thank all the authors who have been part of this poster. So we know technologies like 18 nanometer have specific performance booster, majorly embedded silicon germanium, which are used to boost the performance of specifically PMOS devices, which tend to be normally be slower ones. As a result of this addition of boosters, they are specifically impacted by the layout context, specifically the stress effect, which are forcing the technologies like 18 nanometer to move to continuous RX approach. So if we look at the image on the left, we see that's a classical layout where we have break in the active when you want to design different connection between source and drain. Whereas if you look at the image on the right, you see the active is not having a break anywhere specifically for the PMOS, which is a topward device. As a result, the continuity in the active is still enforced by adding what we call as the gate tie or the tie gate constructs, which is like tying the gate to a specifically VDD supply for a PMOS, which virtually turns it off. As a result, it breaks the connection between source and drain. So this is something which can be managed at the standard cell level, or you can at the cell level, and the simulation will be taking care of that. But we know standard cell is going to be placed in a very, very random context. It's a digital implementation which is being used with the standard cell. So if we are saying that the introduction of the stresses like embedded silicon germania is impacting the performance by the layout context, it means the standard cell which is placed in a very, very different context will be impacted by a variable performance. If we look at the curve, I mean, just to look at the extremes over here, we do see that the performance variation can be as high as 15%. Just to explain the curve further, let's say we have a simple layout which was not having any context around it, whereas we simulate the same layout with different kind of scenarios. One, what we call as the fast context. So the same cell gets abutted to another cell which is having a transistor W, which is full transistor width. Another scenario where it gets abutted with the transistor which is of the smaller W. Another last scenario which is an extension of the fast context where the transistor gets abutted to a cell which is having a very, very long source and drain. As a result, the DUT or the cell under test is going to have a variable impact on the performance in each of these scenarios. And that's what we have simulated over here. So it's normalized with respect to the no context. And we do see the green curve, which is in fact the slow context, which was an abutment with the slower or the smaller transistor width. And the one on the right, which is with the faster context, is with the maximum W. So we do see that based on the width of the cell, because the length of source and drain is varying, there is an impact on the frequency of each of the cell or the delay of the cell. It can be very faster, it can be slow also. So it is important the behavior and the timing is managed in the characterization as well as the impact is taken at the sign-off level. So in order to do that, so we have done three different aspects on this scenario. First, we have extracted the layout netlist of the same standard cell in two different contexts. One, the fast context and the slow context, as I explained in the previous slide. So that is with respect to the post layout netlist extraction. The next thing is that we need to manage the timing or how the cell is behaving in the real environment. So we do have different kind of sign-off PVT conditions. There will be PVT conditions which will be used for hold sign-off. There will be PVT conditions which will be used for frequency sign-off. So we know for frequency sign-off, if the silicon gets slower, that's a more critical point because we will not be able to reach the desired performance. And for the hold, we don't want the cells to get too fast, otherwise we will be violating the hold checks. So for the hold or the hold PVTs, we have taken the fast context where the cell will be the fastest. And for the PVTs which are critical for timing or setup paths, we have taken the slow context for characterization. Lastly, so these two things take into account the two worst scenarios. But however, the layouts will still be subjected to different configurations which will be somewhere in the middle. So to manage that, what we have put is what we call as the edge properties, where we have done the binning of each of the edges of the cell. So we have read the left and the right boundary of the cell from left to right to 3 transistors, because till 3 transistors we know there is a severe sensitivity to the impact of source or drain length, and same on the right side also. Based on the amount of W which is there on the boundary and on the next 2 transistors, we have quantized them into W max, W min, W small. So the cells with the same edge property can get abutted without any issue, whereas the cells which are with a different edge property require a dedicated filler which are inserted by the PNR flow itself. As a result, all the variability in the timing is managed. So in nutshell, I would say the impact of continuous RX we analyze in detail by taking into account the various layout contexts. We manage the impact of this variable timing or because of the context at the sign-off level by having two different netlists of slow context and a fast context, and then correctly mapping it to hold as well as the timing critical PVTs. And lastly, we took care of the edge properties where we assured that whenever a different kind of cell gets abutted with another cell, the placement is accurate and there is no issue with it, or there is less variability what we see on CAD versus silicon. That's it. Thank you.
All right. Thank you very much. Sure.
So I have a question. So since as you said, right, the context is dependent, which right now for the advanced node is, quite a popular, and you can see this in the sign-off. But as you said, is you actually need some like a detailed placement or some placement changes to improve that, which generally means you're going to do lots of last-minute ECOs, right? And sometimes you may not even be able to do that. So of course, the other way you can just do it bring early in the flow, right? But then there could be a PPA impact because this would definitely add additional constraints, on the placement. Mm-hmm. So how do you handle the balance between the two?
I didn't get the two.
Like one is you do you finally try to sign off. You do the last minute ECO, right? But then you probably can only do very few changes to bring your context better, right? Or you can bring probably early in the flow. But then you may need to leave some extra margin.
Yeah. So all the edge property and the following constraints are taken at the beginning of the flow itself, because in the left you have these properties already taken care. As a result, the techno left is assuring that by default, a same cell will not get abutted to a different cell directly, but a filler will be inserted at that time itself. So it won't be an ECO, but the placement by default will be smart enough to manage that. And today, even the design rule or PDK has been updated to take into account that sign-off, that these rules are followed as rigorously and not just at the techno sign-off level.
How many placer or filler cells do you wind up with in this kind of a methodology?
If it is simply two cells getting abutted with the two different transfer widths, we are adding one pitch filler.
Yeah, I understand what you're doing, but my question is you do a design with a zillion instances, how many filler cells wound up there because of your placement issues?
So I don't have those numbers with me.
Okay. My related question is, there's also context dependence for the wiring above the cell. Do you think a methodology like yours could work in that sense, or is that because you don't actually know that context until post-route, you'd never be able to figure that out?
So your question, I would say, is more associated with the top-level routing impact on the standard cells?
Yeah, basically metal 2, depending on where your top level of your cell is, if there's a sea of metal 2, the capacitance of the cell will be different as opposed to there's just one little bit there.
So for that, we know the vertical coupling is very, very low compared to the lateral coupling. And we know that the standard cells normally have a metal 1 or metal 2 as the worst case, and the lateral coupling is already managed. It's not part of this paper, but for the lateral coupling, the layout view itself has a metal 2 dense structure put on top of that. So the worst capacitance is modeled inside the netlist itself. But the vertical coupling is not so much impacting the timing. That has been analyzed.
All right, let's give Rohit a round of applause. Thank you, sir.
Thank you.
Last up in today's lineup, but certainly not least, is front-end analog design automation an NP-type or simply a P-type problem? Please welcome Rami Iskander from Intento Design.
Okay, so I will try to show that analog circuit sizing is not an NP-type problem as was claimed since 80s, and it is a P-type problem. But in order to reach this conclusion, I will raise many questions first, and then I will conclude the presentation. So let's look at the SPICE simulator today. It has a computational model, but we don't know if it was a complex model or not. So what we have done, we know that since we have a simulator, so we can consider it as a P-type problem, because we solve the problem and we can verify by simulation in polynomial time. And the complexity today of the simulation is almost linear. So what we have done is that we have taken the DC algorithm that not everybody knows, and we have drawn the graph that corresponds to this algorithm. So we see very well that it is a way of being just simple graph actually. because there are computations on each branch, and there are communications back and forth between each branch, and all this happens in only one iteration. So SPICE computational model is not so simple. Next, is hand design is superior to optimization engines? The answer is yes, and this was proven by the professor Rutenbar, who he was really in this article honest enough to show that even with by distributing the computation over 200 computers to size a Miller op amp, he couldn't reach the accuracy of a hand analysis, hand design. So again, hand design can always be superior than optimization. So to solve this problem of P and P, we see that we have a design task that is the inverse of the simulation task. We could solve the simulation task, but we don't know how to solve the design task, despite it's the inverse. So it has taken years to reach this solution. So we found that there is a solution for this problem, but it cannot be unique. I mean, the solution, the answer should describe, it should be a model, it cannot be a numerical value. It should be a model that describes all the set of possible solutions. So we came up with two concepts. One concept we called the design graph. We showed that we can take any analog circuit, we create the design graph, so the solvability was approved, and the graph is almost faster than linear because the exponent is less than 1. And then we take the outcome of this design graph, the inverse one, we inverse this graph, we create the simulation graph, and this one we showed that we can cover the transient behavior of the same circuit with the inverse graph. So we could solve this equation by having one model and its inverse. So, and this was the secret behind this. We were inspired really by the human design perception, because the human, when he designs these three transistors, he do it in a sequential manner. So he takes the first one, he computes the width and the voltage, he propagates it to the second one and the third one. So the human model of computation is much, much simpler than SPICE. And the secret behind this is that the human does not compute Jacobian matrix. This is the secret behind this change. So we were able in Intento Design to develop an engine, a solver, that takes an unsized schematic and creates automatically in a few seconds the design graph that is capable of designing your circuit with the precision of a PDK in a few seconds. So today we are capable of sizing 100 transistors in like 40 nanometer in 3 minutes with the SPICE accuracy. And this is what we have done with ST Microelectronics. So they gave us a task to reduce the size of a die area by 20% in 3 months, and they wanted to keep the same noise, power supply ejection ratio and settling time, and to have a lower power reduction. In 4 weeks, we have doubled the production of this wafer. We have doubled the number of die photos on the wafer, and we got very aggressive performances in terms of noise, power supply, and settling time, and so on. So we got an agreement for it's now in production at ST since 2019, and with 50 area reduction and 66% productivity gain. So with the existence of this graph today, we know that the front-end design automation should be considered as a P-type problem. Thank you.
Thank you, Rami.
So I guess my question is, front-end design for analog, to my understanding of it, is not typically done as, let's just assemble transistors in a algorithmic manner. It's more a case of, I want a current mirror, so I just drop in a current mirror, or I want a sense amp, so here's a sense amp. And then the real work in analog is optimizing the back end of dealing with the infinite loop between I generated something, I did some layout, I extracted the parasitics, now that doesn't do what I thought it was going to do in the original SPICE netlist, so I tweak everything and start again. So you described the front end problem, and yet your results are effectively solving the back end problem. So I'm curious as to where
Exactly.
how you did the back end with this.
No, in this experiment we didn't do the. In this experiment we didn't do the back end. Actually, what happens is that we localize very quickly with this graph the best DC operating point, okay, and then we get the dimensions. And lately we did with a German partner, we take these dimensions and we pass it to the layout generator, we create the layout, and then the parasitic of this layout, we get it back and feed it into the test bench where that we need to measure the performances. Okay, so the graph, even if it doesn't contain parasitics, it helps very quickly to localize the design in the design space. And we have a complete cartography of the design space. We know which point is feasible, which point is not feasible, thanks to this graph actually. And the one particular innovation was done in the years of 1800, not there was a German mathematician who showed that he can explore the space by changing only one variable at a time. So with this graph, we just change one at a time, and we are much faster than parallel processing.
Is there, whenever you do that kind of an approach, though, you run the risk of hitting into some kind of local minima that you can't escape from? Is that something that you encountered?
No, because this graph acts as a filter. All optimization engines, you will fall into the 90% of unfeasible space. But the fact that you have this guided search with this knowledge, you are looking on your design in the 10% feasible. So most of your attempts are feasible. The fact that you inject knowledge in your flow, it changes everything. So speed, in terms of speed and robustness.
So you earlier you showed one of the chart like here's a round 1, round 2, round 3. Here's a best solution, which is a human, the manual solution.
Can you repeat, please?
Okay. So in one of your slides, you showed you got a round 1, round 2, round 3, and then the human solution, right? So with this new approach, how do you compare? Because analog generally they always compare to the best designer manual approach, right?
How I compare the human?
Yeah.
I with this solver creates exactly a replica of the human mind that we have. For example, for example here, you have M3, M1, yeah. The designer was going to say to size M3, M1, M5, and M8. This is what you have here on the graph. Because we are capable of generating the exact replica of the designer process.
So it sounds like you're now just front end part. You're doing also sizing, post layout. I guess there's some just robots, some back end optimization as well. Sounds like embedded in.
Yeah, I mean we localize the design and then we give it to a layout generator to see if the effect of layout dependent effects and the interconnect parasitics.
Because the back end loop, sometimes you discover that the thing that looked good in the front end turns out to be not so good, because once you start dealing with variation in the transistors or
even the size of the width, you can get a width that is smaller because you have a contact that cannot. You can have a lot of, so it's preferable to take the dimensions. We call it electrical dimensions, and to pass it into the physical dimensions.
Yep.
This is what we.
Yeah, and then to try to achieve the physical dimensions is not always easy.
Yeah.
Okay.
Let's give Rami a round of applause and an extended round of applause for all our presenters today. Very nicely done.